and I want to formally welcome all of you to the Autodesk Design and Make webinar series for educators. This is a brand new series. This is webinar number 1 that we're super excited to be kicking off with all of you this afternoon, or again, good morning, or wherever it is, whatever time it is, wherever you're coming from. We see that we have folks from all over. And this first webinar is called Get Started with Tinkercad Circuits. But before we do, I want to do some introductions, let you know what we're talking about and all these great things. So my name is Jason Erdreich. I'm a technology and engineering educator, and I've teamed up here with the Autodesk and Tinkercad teams to provide webinars and training things like this to teachers like you. And it's been really exciting to be able to be working on these projects for some time now. And I'm joined as ever with my co-host, Randy.
Hi, I'm Randy. I'm on the Autodesk team on education, and I primarily work on Tinkercad and Instructables. And I know the other folks aren't on the slide, but we also have Nicole, Kellyanne, and Josh who actually built circuits. So we have a special guest tonight with us.
Yeah, absolutely. And I'm glad you brought that up, Randy, because I always love to say a huge thank you and a huge shout out to the whole Autodesk team here. So Randy and I are, of course, the people that you see now, but like you mentioned, we have a bunch of folks behind the scenes joining us here tonight, Kellyanne and Darren and Josh and Nicole, and they are going to be working pretty quickly in the chat and the Q&A to answer all your questions throughout the evening, as well as the session. And there's also a much bigger team that's helped us bring all these awesome things to you. So big thank you to the whole Autodesk and Tinkercad team. Now, the Design and Make series for educators. So as I mentioned, this is a brand new series that we've sort of combined by culminating the previous thing. So you may be familiar with the Teaching with Tinkercad series that we ran in the first half of the school year, as well as the Level Up with Fusion series that we also ran in the first half and kind of leading into 2024. And from that, we've really decided what could we do to engage and excite students from a really diverse collection of subjects, as all of your teaching, because we have folks coming from all over the education spectrum here in grades. So this is really going to be a culminating series to combine really just about everything students can create with the very diverse Autodesk programs, talking about Tinkercad, Fusion, all these great resources, and bringing in career connections to, of course, excite and engage our students as they really do design and make just about anything. Now, this series is going to continue through the remainder of the school year for 2024, and we're going to be meeting every other Thursday, give or take. Some holidays and things might adjust that a bit, but in general, every other Thursday at 7 p.m. Eastern Time or 4 p.m. Pacific Time. And as I mentioned, tonight is all about Tinkercad circuits, which I'm super excited about, something we know a lot of folks have been asking about, and it's one of my personal favorite features of Tinkercad. And looking ahead to next webinar, that'll be on February 29th, and we're calling that one Leap Forward with SimLab. We did a Teaching with SimLab webinar way back when at the start of the year, and we know a lot of folks really enjoyed it. But since then, there's a lot of new exciting features that we're really excited to showcase and show off to you in just 2 weeks' time. And of course, you can find out more about the upcoming webinars and all these awesome features all over the webinar page and the Tinkercad blog. So we're going to drop a poll on your screen right now. And this poll is going to kind of try to gauge your experience in teaching with Tinkercad. So you should be seeing that any moment. And if you could let us know what your experience is, whether you've been teaching with it for some time, if you're just getting started, if you're an expert with Tinkercad, we love to know that, because as we go through some of the demonstrations and as we kind of talk about our different things, we want to cater this as much as we can to you and your needs. And as you do this poll, I'm going to answer a couple questions I see popping up in the chat. So these webinars are recorded. We record these each time. So all the previous webinars that I mentioned, the Teaching with Tinkercad webinars, the Level Up with Fusion webinars, you can find those on the Tinkercad YouTube channel. And I'm sure one of my awesome team members are going to drop them in the chat right there, which is fantastic. So you can find them there. And yes, this webinar is being recorded as well. So you can always go back and recap this one. So I think we've just completed our poll here. We're seeing a ton of folks that are either just getting started or some experience, but wanting to learn more. And that is excellent, because you are absolutely in the right place and the right time. But I also see that we have a handful of folks that are experts on things, which is super great. We're definitely going to be getting into some of the more advanced features. I always talk about circuits tonight. So that's really exciting. Now, before I dive into the content, I just want to give you a quick overview of what the format of this webinar is going to be, in case this is your first one. So the chat is a very active place, as you can see. Lots of folks are giving us feedback and things like that, which is fantastic. Please continue to do that throughout the webinar. But we also have a Q&A feature. So there's a Q&A button that you should see on your Zoom toolbar. And if you ask a question in the Q&A, it kind of sticks there and it stays there until we answer it. So that's really a great tool to use. So that way the Autodesk team that's with me right now can go ahead and answer your questions. And then you can actually also go back and find those answers instead of the chat that kind of scrolls sort of quickly. So throughout the evening, please go ahead and use that Q&A feature. We'll be dropping links and things in the chat for you to take advantage of. And then at the end of the webinar, before we say goodnight, we're going to dive into a live Q&A where you'll be able to ask questions to our team using the Q&A feature, and the whole Autodesk team will be here to kind of recap and answer your questions that you have. So that's something to look forward to as we go on. And I also just want to remind you that, again, the Zoom's being recorded, and these slides that you see will also be shared with you in addition to the recording. So what is Tinkercad? I see that we have some new users. So in case you don't know, it is a really diverse program that has 3 primary design features. So we can do 3D designs, circuits, and code blocks. 3D designs is definitely what Tinkercad is probably predominantly known for. So this is the 3D editor where you can manipulate shapes to create just about anything as you design 3D models, different scenes, artscapes, and as I mentioned, some newer features like SimLabs to do physics simulations. And we're not going to be talking about this feature very much tonight. But again, you can find out a lot more information about the 3D design feature via the Tinkercad blog or past webinars that we've run. And future Design and Make webinars will absolutely focus on a number of features in the 3D editor. We have the circuits feature, which I'm not going to talk too much about now because that's the whole goal for tonight. But as you can see, we can make electronic circuits, but that's what we're going to be diving into in tonight's webinar. And then we also have code blocks, which is something that we did in the Teaching with Tinkercad series. So you can go back and check that out. But it's essentially creating 3D models with a block-based or visual coding language, which is super cool. So bringing in, I see that we have a lot of computer science teachers with us tonight. So this is a great way to kind of incorporate that STEAM concepts, 3D design with code, and you can even bring your coded models into the 3D space. So really cool features that you can do while teaching the concepts of computer science. Now, Tinkercad is accessible via the browser or an app. So if you're working with something like an iPad, there's a great app that you can do on the tablet. Or if you're using a browser, you can access Tinkercad on any device, Chromebooks, Windows, Macs, whatever you have in your classroom is perfectly acceptable to work with Tinkercad. Teachers and students can access Tinkercad completely for free. It's free for everybody, but there are specific accounts for teachers and students. So you as a teacher can either create a free account or sign in with a supported account like the ones that you see on the screen. And as a teacher, you have some powerful features to do things like create classes, create activities, manage your student accounts, and students can also sign in, again, using a supported account if your school uses any of these, or they can create an account as well, depending on how old they are, or you as the teacher even have the ability to create student accounts and manage them entirely. And we talked a lot about this in that Teaching with Tinkercad series. So if you want to learn more about those things, again, we dropped that link in the chat. Please make sure you go back and check that out. Now, I've mentioned this briefly. Classes and activities is a really powerful tool for you as an educator to be able to kind of group your student work together. You can create what's called an activity, which allows students to kind of share their assignments or share their projects specifically for that activity. And the cool thing about activities is this is also a way for you to provide work. So if you want to give them a template to start from, you can do that. And activities is compatible with all 3 of the spaces in Tinkercad, the 3D designs, circuits, and code blocks. Something very new that we're super excited to talk about is Tinkercad Challenges. So this is a new button on the side of Tinkercad. When you're looking at the Tinkercad screen, I'll point it out to you when I'm demoing Tinkercad earlier. These are challenges designed by the Autodesk team to give students themed projects. So for example, creating a gingerbread house or creating a landmark, something specifically with SimLab, whatever it might be. And this is a really great activity that's real world, connectable to careers and different themes and things like that that might tie to your content and curriculum. And students can choose to actually not only do the challenge, but submit their projects and collaborate with the Tinkercad community if they'd like to do so. So that's a newer Tinkercad feature that we are really excited to be seeing. And I keep mentioning Fusion, and we have a Fusion series. Fusion is a more advanced Autodesk program, and Tinkercad can seamlessly send projects to Fusion with a click of a button. So if you want your students to be able to elevate their designs with some more advanced features like animation, rendering, and a lot of the things that we've talked about previously in other webinars, this is a great, powerful transitioning tool, especially as I'm looking at, we have quite a few high school teachers. This is a great way to transition from Tinkercad to Fusion as students get older. So Autodesk Design and Make, as I mentioned, there's so many different resources, and tonight we're focusing on one key resource for designing electronics and circuits. But this webinar series over the next number of weeks till the end of the school year, we'll be talking about a lot of these different concepts as we dive into really diverse and creative projects that your students can be challenged to do with all these awesome software resources. So that being said, I think we can dive in here with circuits, our theme for the night. And again, if you have any questions about Tinkercad or the things that I just mentioned, please drop in the Q&A. I know I have my team here that's excited to give you the support that you need. So I'm going to demo this live. So I'm going to pull up Tinkercad here, but I just want to point out that everything I share live actually has a slide. So we're going to share the slideshow with you along with the recording tomorrow. And you can always go back and you'll notice that each thing that I'm talking about has its own detailed slides with the vocab. So that's a resource that's going to be shared to you, even though you're about to see me demo everything live. So I'm going to switch my screens over here. Let me just switch to Tinkercad. All right, so I've already signed in, okay? And I'm looking at a teacher account. So as a teacher account, I have this classes button, and this is where I mentioned you could create a class and create an activity, and your students could actually submit projects specifically to this activity if you wanted to do that. Or as a teacher, again, you could actually create student accounts so you can kind of manage them and things like that, which is excellent for our youngest students, which is exciting. And then this is also the challenges feature that I mentioned, where you can actually view ongoing challenges and things like that, and then just start tinkering and start designing one of these active challenges, as well as viewing past challenges. So if you're just a teacher looking for some awesome themes and awesome projects, definitely check out that challenges feature. Now I'm going to switch over to my designs feature where I can see I have 3D designs, circuits, and code blocks. And to make a new circuit project, I just click this blue create button and then I select circuits. Now, the circuits editor, the circuits design space, looks quite a bit different from the 3D design space, but there are some similarities. The first is that you get this, this name that's created just like before. And if you want your students to name their project, they can easily click up here and rename it as they so. We also have this top toolbar, and we have a design space in the middle. When I want to create electronic circuits, I need to use what's called components, and that is what I see in this sidebar. Now, by default, I'm not looking at every component that's in Tinkercad circuits. I'm looking at a collection of really common components, but you can use this dropdown to switch between all components where you'll see many different electronic things, or you can, of course, browse by a particular project. So for example, if you're going to work specifically with like an Arduino or a microbit, there's also starter projects. We'll talk more about that as we go, but I'm going to keep myself in the basic components. Now, in order to have success with circuits, we do need to talk a little bit about the fundamentals of electronics. And while I'd love to go really far into high school level physics and Ohm's law and everything tonight, I know we don't have time. But I'm going to try to cover the basics to make sure that we understand what we need to do here. So in order to have a successful circuit, we really need 3 components. And the first is a power source. So I might grab, for example, a battery. So I have this coin cell battery here. The next thing I need some type of load, which is something that would actually be powered by the circuit. So for example, I might want to turn on an LED with this battery. And you'll notice I'm just dragging these components out into my design space. I can move them around when they're in the design space. Components have different properties, right? So you'll notice that on this battery, I could actually number this. So if I had multiple batteries, I might call this battery number 5. And then for my LED, the property window looks slightly different. I can name the LED, but I can also change the color, right? So each component's going to have different settings depending on what the component is. So let's make this LED green. Now, after I have a power source and I have a load, I need to connect these components together to allow the currents or the electrons, the power, the electricity to actually flow. And we, of course, do that in the real world using wires. And we can do that in circuits as well. So when I click on any of these contacts, these terminals here, you'll notice that they highlight. So this is my positive terminal and my negative terminal. And what I can do is I can click on this and a wire is formed. And I can just go click on another component here. So I could snap this to a component like that. Now, if you want to make an organized wire, you can actually click and keep clicking, and you can kind of make bends in your wire, which is super cool. You can also change the color of the wire, so you can organize your circuits accordingly with different colors. And there's different types of wires. So for example, this is a standard wire, which is sort of like a wire to wire. But you'll notice I actually have this drop down right here to change between a hookup wire, which is what you would use for maybe some different tools and instruments, or alligator wires, which realistically, if I was going to build this in the real world, I would probably use an alligator wire to clip these things together. Now, circuits is a fantastic opportunity to not only learn about electronics and learn about the things, the fundamental things we're talking about tonight, But it's also a great way for students to experiment with electronics in a safe space, right? This is all virtual. This is all digital. So if I accidentally hook something up wrong, nothing's going to fry or blow up or explode or, cause any harm on my workbench. So I love using circuits personally as a teacher to allow my students to prototype their circuits, to experiment with this as we lead into then building and creating things in the real world, because these really are real components that we could actually purchase and assemble within our classes. And it's a great opportunity for students to make mistakes, like so. So I'm going to hook up 2 wires. All right. And I'm going to go ahead and hook this up like this. And I have 2 different color wires. Technically, red is usually the color used for positive in a DC electronic circuit, and black is what we typically would use for negative. And you'll notice that my light's not turned on. And there could be a couple reasons for this. The first is because I haven't actually sent any power to my circuit. So what we're in now is that I am in a build mode. So when I'm dragging things around and moving wires like this, I am building. If I actually want to power my circuit on, I would hit this start simulation. And we'll notice that my light doesn't come on. And I love doing this, right? The reason is I made a mistake. Now, I know I made a mistake, but again, when you're designing this with students, and I often am asked, why would we do this on the computer? Why would we not just do this on the workbench, right? We're doing experimentation and circuit design in a controlled space. So I can simulate things, I can test things out, I can see if things work, I can see if something goes wrong where I know everything is controlled. I know this battery is charged, it has voltage because it's a simulated battery. So then I can troubleshoot, okay, maybe I did something wrong, and I can go back and I can diagnose my circuit. So I mentioned this briefly. The issue that we have here is in circuits, something we need to consider is called polarity. And I know I'm going over this kind of quick, but as I mentioned, this is being recorded and there's a lot of notes with detailed slides here. So for our circuits, we know that we need a power source, which we have. We know that we need paths for our current or the electrons to flow through, which we have. We know we need a load, but we also need to make sure that we're actually hooking this up correctly. So I'm going to simply delete these wires real quick. And we're going to look at these contacts a little bit more closely. I can see that my battery is labeled positive, which is red, and negative, which is black. My LED doesn't have black and red, which is why I just assumed I can hook it up however I wanted. But if I hover over the legs for the LED, we'll see that one is labeled cathode and one is labeled anode. So cathode is another term that we would typically describe as our negative contact, when anode would be the positive contact. And the reason that this didn't turn on before is because I hooked up my cathode to positive and my anode to negative. Now, not every component is polar. So for example, if I were to grab a switch, this one is just called terminal 1, common, terminal 2. This is not a polar component, which means it doesn't matter where I put my switch. Buttons aren't polar, most motors aren't polar, but many components are. And Tinkercad Circuits does a really nice job at labeling when you have polarity. So as students are not only learning about these components, right? If you actually pick up an LED in the real world, it's not going to magically tell you positive and negative, right? But in circuits, this is a great learning experience because it shows us how things should be wired together. So let's fix this circuit and let's make it a little bit more advanced. I have a battery, I now have a switch, I have an LED, and we actually want this LED to turn on. So there's a bunch of tools up here that I haven't used yet. One of them is a rotate tool. So if you want to rotate your components around, you can like this. And another is a mirror tool. So if you want to flip your components like this to mirror them, you can do that as well. So I'm going to hook up and I'm going to use the normal wires for this. I'm going to hook up my negative with a black wire to my cathode like that. And then I'm going to hook up my positive through my switch. So I'm going to hook up my switch like so. Okay. I don't have another component here, so I'm not going to be using every port on the switch, but that's perfectly fine. When I power this and I run my simulation, we can see that my LED is on. And if I click on my switch, we can see that it turns off. So we've just illuminated an LED. And if I were to actually build this in the real world with the same components, it would illuminate just like this, which is really exciting that we get the chance to get hands-on and experiment with our circuits. Now you notice that we have a little warning here. So this is telling us that, hey, you built a circuit, but you have too much current flowing through. So again, as we simulate our circuits in Tinkercad, we can actually test things out. We can see what issues we're going to run into before we build this in the real world. So if I wanted to actually fix this, what it's saying is I need to add what's called a resistor, which reduces the flow of current. Now I can adjust my resistor values, right here in the properties menu. So I have a 1K or 1000 ohm resistor. I could increase this or decrease this. And resistors are non-polar. These stripes here are actually showing you the amount of resistance. So that's actually a color code to show you. And so that, for example, these colors, this brown, black, and red matches with 1K. So when you actually go ahead and build this in the real world, you would find the resistor with the same color stripes, and then you have a chance to actually build this. So if we throw this 1K resistor in, and because it's non-polar, it doesn't matter if I put it on my positive or my negative, we notice that I don't have a warning anymore, which is super great. We'll also notice that the light's a little dim. And the reason is now I have so much resistance that my light's a little bit more dim. And to give you a quick analogy about what this might be, imagine that you have a garden hose with water flowing through the hose, right? The hoses are wire, and the flowing water, the water molecules, is kind of like our flowing current, or flowing electrons that's going through the wire. If you stand on the hose, you don't change how much water pressure is. You don't change the pressure in the house, but you do reduce the flow of water. And if you stand on the hose really, really hard, it'll actually stop flowing the water altogether. That's kind of what this resistor is doing to my electronic circuit, is it's not changing the amount of voltage in my battery per se, but it's reducing the flow of current. And I've reduced it so much that I have a very dull or dim LED. Let's click on this resistor and let's change this. Instead of being 1000 ohms, let's make it like 250 ohms. And let's watch our LED. It's much brighter, but no warning. So now I know that this is a much more successful circuit. I have a bright LED. I don't have any warnings from Tinkercad. So this was a great prototype circuit that I could then go and build this in the real world. Now, the really cool thing is Tinkercad will not only give you warnings, it does simulate a little bit of what could go wrong with your circuit. So for example, if I were to grab a 9-volt battery, right, let's hook this up the same way. I won't do a switch this time. All right, I have a 9-volt, and I'm just going to mirror my LED so it lines up. So I'm going to go a negative wire to my cathode and a positive wire to my anode. And when I go and run this, our LED blows up. Way too much voltage, right? Way too much current passing through. Way too much current passing through our LED that this would just fry the LED. And that would happen in the real world. It doesn't look like this nice cartoon. Poof. It's more of a very subtle light goes out. But it's a really nice chance for your students to see like, oh, wait a minute. If I did this, I would totally be frying my teacher's LEDs. So again, I can use circuits to say, hey, maybe I need that 1K resistor in here to see how this goes. Yeah, that's much better. That's a much more successful circuit, right? So this is a great prototyping opportunity for students to work with. Now, I keep working with exclusively LEDs at the moment, but I just want to point out that there are so many components, right? So perhaps you actually want to power on motors or things like this. You might even want to be able to prototype and test your circuits and see how they would work. So for example, let's grab a AA battery. And I love this drop down specifically for the AA battery because look, you can choose to switch it between AA or AAA, which is super cool. You can also choose to switch it between 2, 3, or 4 batteries. And if you want, you can even add a built-in switch, like one of these switch power packs. So really cool features by the Tinkercad team to allow you to again create like real world circuits here. So if we wire this motor up like so, okay, negative to positive, I'm going to run my simulation, and we can see that my motor is spinning clockwise at give or take 6,000 almost RPM, which is super cool. If I wanted to, I wonder what would happen if I actually reverse my wires here. So I'm going to flip-flop my wires here. That's interesting. Now it's spinning counterclockwise at negative 6,000 RPM, right? And that's because while motors are often labeled, a DC motor like this is reversible in polarity. So if you hook it up one way, it'll spin clockwise. If you hook it up another way, it'll spin counterclockwise. That's kind of unique to DC motors, right? Servo motors and stepper motors, those are a little bit different. We'll talk about those later on. But like these hobby motors and things like that work really cool in that way. So again, we're experimenting with electricity as we go ahead and as we build. Now, I just want to show you a couple other cool features. If we keep looking a little bit farther through our components here, you'll see that we have a lot of different LEDs, a lot of different motors, a lot of different components and things, and we'll get into programming in just a little bit. But even you have things like a solar panel, which is really cool. So you might have students prototype the circuit for like a solar powered car project or something like that. And one of my favorites is you even have things like a lemon battery and a potato battery. You also have electronic instruments to allow you to interact with your circuit. So for example, I keep talking about current, voltage, resistance, right? These aren't things that we can see, right? Such a small thing, electrons, but we can measure them, right? So in the real world, you might use something called a multimeter. And we can actually use these tools in Tinkercad circuits. So I can hook up my potato battery to my multimeter like this, and I can measure that, all right, this potato battery is giving us about 670 millivolts. I can say how many amps we have. I can check resistance, which is really the resistance between the connection, right? But I can see that we have roughly 670 millivolts here. So if I wanted to, let's say, build a bigger battery and test this out and maybe power something, let's grab a few potato batteries here, maybe 4 potato batteries. I could actually create a series circuit. What would happen if I connect 4 batteries together in series like this? And let me grab my multimeter again. Here we go. So we had 670 millivolts before. Now I have 4 potato batteries working together. Let's see what we did to our current. All right, you'll notice that I keep zooming in and out in the workspace, so you can use the same kind of Tinkercad tools to zoom in and out with your mouse wheel and select things and pan around. And if you ever want to make your design fit, so if you get kind of lost like this because you have a really big design, this button right here in the top left corner, or F on your keyboard, will make your entire design fit. So we have 4 batteries now. Let's see what we have. Cool, we're almost up to 3 volts. We have 2.68 volts, and I wonder if we can power an LED with our potato batteries. Let's find out. All right, so let's see. I know that I'm not doing a great job with color coding my wires right now, but that's okay. Potato battery powered LED? I think so. It's dim, but I think it's there. Let me toggle the simulation on and off. Definitely on. We have a nice dim LED with our potato batteries. So that's really cool. And what we're building right now, everything we've done so far tonight, are called analog circuits, right? So we're using analog components, no like digital controllers or things like that or code yet. We're going to get to that. Analog components to create custom circuitry, which is really fantastic. And again, there's so many different components that you can use. There's also a lot of integrated chips, integrated circuits down here that you can use and work with as well, which is great. A lot of different types of transistors and really complex components, relays and things like that. So you can really make a very wide range of projects. But let's make something a little bit more advanced, like potentially a project for a real prototype here briefly. I'm going to grab what's called a breadboard. So this is a really powerful tool if you actually want to build a component together, right? So far you've seen me just kind of connect wires from component to component, bit of a wired mess, which is a great way to learn. But if I was going to build a lot of things together, if I want to combine a lot of components together, let's say more than one LED or an LED and a motor, how would I actually hold all these wires together in the real world? That's what a breadboard's for. And as I've taught breadboarding, I have found that my students struggle to often learn how to use it. And the reason is there's a lot of holes, right? There's a lot of places. It's very easy to accidentally put something in the wrong location so that way your circuit's not connected. I love that Tinkercad, when you hover over this, it shows you how the breadboard is interconnected. So for example, every space here in this first row, columns A through E, are connected to one another. So if I, for example, wanted to put an LED, and I'm going to rotate this around so it fits in my breadboard like this, and I wanted to connect that LED to, say, a push button, and I'm going to rotate this around so it fits like this. What I could do is I could actually run a wire from row 2 to row 5, and these components are now connected. And the reason is, if I hover over this, we can see that this pin on my LED is in the same row, so that's connected to this pin, which runs to here, which then runs to my button. And that's really difficult for students to learn. So by doing this, by prototyping, by breadboarding here in Tinkercad circuits, it allows them to kind of see how these things go and really give them a map to then look at their screen and then go and build it in the real world. It's an excellent starting point. So let's make this slightly more complex. I'm just going to grab a quick resistor like so. We're going to make a little bit more of an advanced circuit here, not 220,000 ohms, just 220 ohms. There we go. All right, so I have my cathode running to my resistor. Again, this whole row is connected. I have my anode running to a switch. And then what I'm going to do is I'm going to run my switch down here to the positive column. Now you notice on the side, this entire column's connected. So anywhere on this column, and it's labeled positive, you don't have to put positive here, but it's a good labeling tool. So what I'm going to do is I'm going to run my battery around like this. And now this red wire is actually connected to this red wire because we're in this same column, even though it doesn't matter which hole I choose, right? I can be here or here as long as I'm in this same column. I'm going to run around. I'm going to run my negative wire. I'm going to try to organize this well with color-coded wires. And what I think I've done is I've created a connected circuit. So we have our negative come into this negative column. That then flows to this resistor, which flows to this row, which then flows to my LED cathode, which then flows here to my positive wire, which then comes down to my switch. Okay, my switch is connected like this, where it runs across. And I think this is going to work. Let's push our simulation and let's click our button. And we have a lovely LED that turns on. You'll also notice the center divide, the center channel here that breaks up column E and column F. So this right side of the breadboard is also interconnected, but it's not connected to here. If I wanted to connect this side of my breadboard to this side, I could do something like this and run, not while I'm in simulation, but I could run a jumper wire across if I wanted to. If I did want to connect both sides of the breadboard like that, that's perfectly acceptable. Or you might have something completely different on the other side of the breadboard. You also notice that breadboards come in all different shapes and sizes. So there's some small ones, mini ones, big ones, whatever it might be. So this is a little bit more of a professional analog circuit, right? And I might want to go ahead and build this. So I have my simulation, I have my map. The other cool thing that Tinkercad will do is it'll give me a bill of materials or BOM file. So it will actually list right here, and I press this little spreadsheet button in the top right corner. It'll list not only the labels, which is what I can label, the quantity of each component. And I could download this as a CSV. If I was actually going to order these components, I could upload this to an electronics vendor or something like that. Or your students will just have a nice little list of the components that they might need to actually create the circuit. The other thing that I'll create is a schematic diagram. So if I click this button here, if I zoom in, it will use what's called the schematic symbols, which are standardized symbols that's used all over electronic industry. And it will actually create a schematic diagram for me, again with the labels, which I can change the labels if I needed to. And it will show me all my different circuit paths, and this can be downloaded as a PDF, which is really, really cool. It'll have the date, it'll have, everything like that, and the title, which of course your students could rename the title to say, their name, their project. So that's really awesome. So by creating this simulation, not only do we get to test out our simulation, see if it works, we also get some real world files and connections with this by creating schematics, by creating bill of materials, and that's all generated automatically based on your design. Now, we've talked about analog circuits for a long time here, and I think we've covered the basics. So let's dive into some digital circuits. In Tinkercad circuits, we have a couple different microcontrollers. So the first one I'm going to talk about is the microbit, which is super popular in education. Hopefully some of you folks have seen this. It's a lot of fun because it's a very intuitive and easy to use component to get started with. And we can create electronic circuits with the microbit. So for example, let's turn on an LED using our microbit. I'm going to grab another LED and I'm just going to rotate this around. And I could wire this how I would in the real world, which would be using alligator wire. So I would hook up my anode with an alligator wire to say pin 0 like this. And I'd use my another alligator wire to hook this up to ground for my cathode, GND for ground. All right. And then I need to write some code to actually turn on this LED. And the cool thing is you can do that right here in Tinkercad circuits. So we have a programming window on the side that I opened up via the code. You can't open up the code window unless you have something to code. So I needed the microbit first to be able to open this here. And I have the ability to program in a block-based language like this, or I have the ability to program in a text-based language, which for the microbit would be Python. And you could even challenge your students to see both at the same time. So if they're learning in block, that's great. If they're learning in text, they could switch to just text, or they might want to actually design it in block and just see what happens. So if I were to grab a block program here, notice that it actually writes the text code for me, which is super cool. So we'll actually show students how to write in text as they work in blocks. And again, you could type in either one, depending on which option you choose. So the microbit's really fun because it has some built-in features. It has two built-in buttons here, A and B, which we can program. It has a built-in LED screen. If it's a microbit 2.0, it has a built-in speaker. And then again, we have a bunch of different pins that we can work with. It also has built-in sensors. And what I'm going to do is I'm going to program this LED to turn on when I shake my microbit. So if I were to shake the microbit, I want the LED to turn on. So I've grabbed this function that says on shake, and we're going to go to the outputs category and find our digital writes, which is how we would power on our LED. Okay, that's the command that we're using here. And I'm using P0 because that's pin 0. And high would be a high amount of electricity or voltage or current, right? So that's on. Low would be off. So this is saying on start, when my microbit turns on, I want to maybe show a little heart because I love what I'm doing. And then on the shake, if I shake my microbit, I want this LED to turn on. Now, I might also want the LED to stay on. So let's go find a wait here. So let's keep this LED on for 3 seconds every time I shake my microbit. Now, I would just start my simulation just like I would. And you'll notice with the microbit, we get this pop-up window right here. Now, the pop-up window allows us to use the features and the sensors and things built into the microbit. If I want to just push a button, I can literally click right on this. You'll notice I have my heart on my little screen. I could click here to say use A or use B, just like that. Or I could rotate it. This would be using the accelerometer in the microbit. I could adjust the temperature that it's reading. There's a built-in temperature sensor. There's a built-in ambient light sensor that I could adjust. And down here, I can simulate shaking my microbit. And notice, keep an eye on my LED. It's on now for 3 seconds. And if I click it, it turns on. Now you'll notice that it's still on here. And if you look up top, I have a simulator time right here. So you'll notice that my simulator time isn't actually continuing at like 1 second. So the simulator is moving super slow. And the reason being, when you write code, depending on how complex your code is, the simulator might need to process that time, right? So it's important to keep track of the simulator clock. So if you see something not turning on or off, it might be the speed that the simulator is running rather than necessarily the real-time speed. So always keep an eye on this when you get into more advanced circuits. But again, if I run this here, and if I shake my microbit, you'll see that my LED turns on, which is super cool. Now, I'm just going to minimize the code window, right? Microbits can work with a lot of different types of components. And let's say, for example, you actually want to use more advanced things with a microbit rather than just clipping in the LED and things. Microbits, while you can use alligator wires to clip directly to these pins here, pin 0, pin 1, pin 2, and 3 volts and ground, you can also notice that there's a lot of small little pins, and you can use all of these as well if you have what's called a breakout. So if I go back down to my microcontrollers, you'll notice that this microbit, I'm just going to get rid of this guy real quick. This microbit has a breakout board, and this breakout board lines up perfectly with a breadboard. So this breakout board would allow me to still program my microbit just like before, but would actually allow me to program my microbit using some more advanced components, like some different sensors and things like that as well. So microbits are super great, and you can actually program them. And you might be thinking, how do we get our code to the microbits? Well, in the code window, when you download this, and the reason we're not seeing the shake thing is because I'm using a different microbit. If you have more than one microcontroller, you can actually program multiple and switch between them here. You'll see this little download button right here. So that'll actually download the code file, which in this case is a hex file for a microbit, and then you can drag and drop that to your microbit depending on whatever type of device you're on. Super cool. Now, the other type of microcontroller you might choose to use is an Arduino. So I'm going to find my Arduino. Specifically, this is the Arduino Uno, and we also have an ATtiny as well. And the Arduino has been around a little bit longer, quite a bit longer than the microbit, right? It's a little bit more advanced. I would say this is probably more of a high school, middle school, upper middle school type of thing. And on the Arduino, you'll see that we have our pins here. So we have way more inputs, way more outputs. And an Arduino, unlike the microbit, doesn't really have anything built in. So if we want to use a button, if we want to use a sensor, apart from this little reset thing here, you kind of have to wire everything to an Arduino. And you would typically do that using a breadboard. So I'm going to grab my breadboard. I have my Arduino. And I'm just going to go ahead. I'm going to run my ground pin, not using an alligator wire. Let's switch back to the normal wire. I'm going to run my ground pin around to my breadboard like so. And again, the way that I'm getting all these bends in my wires is I'm clicking as I'm running the wire, which allows me to run around like that. And let's turn on an LED, just like we did with the microbit at first. We'll add something else before we go. So I'm going to grab a nice little LED. Let's change the color to something different. We'll make it blue. And I'm going to hook up my cathode of my LED to the ground pin of my breadboard. We know that this is connected to the ground way down here because, again, we can highlight and run this over. And I'm actually going to hook up my LED directly to pin 13 here. And I'm going to actually make this wire blue because it's a blue LED. So that'll keep me nice and color coded. Now, just like the microbit, after I have these components here, I can click this code button, and you'll notice that we have a program pre-written, right? Just like the microbit automatically said, draw a smiley face. So Tinkercad actually provides you with a starter program that you can actually see. And again, just like the microbit, you can program the Arduino in either a block-based language or a text-based language. So you can program this. This would be the C++ Arduino language, which is typically used to program an Arduino. So this default set of code is set to make a built-in LED blink. And I happen to know that the built-in LED should be connected to pin 13. So if we run our code, we'll see that we already have a blinking LED using the default program, which is pretty cool. But I could go ahead and I could modify this a little bit, right? Let's say, for example, I wanted to add another LED. I might grab one here and rotate this guy around. And we need to hook this up to ground like so. And I'm going to hook this one up to pin 12 using a yellow wire. This is my yellow LED. And if I run my simulation, this yellow one won't turn on because obviously we haven't programmed that yet. So let's do that. And I'm going to do this personally in the text language. I know we have a number of high school folks with us here, so I'll program this in the text language. I'm going to make my text editor a little bit bigger, right? And I'm actually going to change this default code a little bit. I'll start with it, but I'm going to change it. First, I'm going to make an int called blue. That's an integer for my blue LED, which is plugged into pin 13. And we'll make another one called yellow, which is plugged into pin 12, which is super cool. I'm going to change this pin mode to say blue. So what this is doing is it's saying, all right, this blue pin 13, is an output. Anytime you're turning something on, that will be an output. Because I'm a little lazy, I'm going to copy and paste this program or this line of code and do the same for yellow. I also love to teach comments. So I like to comment that this is closed setup. And in this language in particular, entering like this doesn't make a difference. So I just like to put some gaps in my lines of code to make it a little bit easier to read. So digital write, this is actually the same command we used in blocks for the microbit, which is cool. We're going to say digital write blue, high, wait 1000 milliseconds. Digital write blue, low, wait 1000 milliseconds. And this is our loop. So this just repeats infinitely. When the blue light is on, I want my yellow light to be off. So I'm going to say digital write yellow, low. So that's going to be off here. I'll comment that off, and then this is on. All right. And again, to make it a little bit easier to read, I'll put some spaces here so you can see what I have going on. And then when the blue light is on, off, we want the yellow light to be on. Now, I'm going to intentionally make an error right now, and I'm going to forget this semicolon. And let's see what happens if I don't have a proper program. Tinkercad tells me. I get a nice little highlight here. Now, this line is highlighted because it's saying this can't be right. And the reason is I forgot a semicolon here. So it expected a semicolon before. So as your students are prototyping in Tinkercad, they're not only prototyping and learning the fundamentals of electronics, they could be prototyping and learning the fundamentals of writing code to control electronics, to do things like microcontrollers. And again, this is all done in a very safe and collaborative space where students can make mistakes, trial and error, run their programs, troubleshoot, to then find success where you have this lovely little blinky type of program. Now, you might be familiar with the Arduino, and then you might also be familiar with the fact that some components, like for example, a servo motor and some different sensors and things like that, a digital LED screen or something like this, needs what's called a library. And you have a couple cool ways to do this. First off, if you're working in the text-based code like this, there's this little libraries button, and you can browse from a wide range of libraries to allow you to work with these different components. So I might hit include, and now I have the ability to program this servo motor if I wanted to. But if you're just getting started, right, and I'm just going to switch back, I'm just going to erase my code, which is fine. And if you don't really know how these components work, you'll notice that there isn't a libraries button for the block-based code. And that's because all of these components that might need a library already have it in blocks. So if you're trying to just get started, you're just learning how the servo works, you don't know how these libraries work or whatever it is. If I go ahead and grab this rotate servo like so, and if I look at my text code, we'll see that it actually wrote the servo code for me and it included the servo library just like this. So that's a great way for students to get started, especially as they're gaining skills in writing text-based code, if they're gaining skills in programming something like an advanced microcontroller like an Arduino, using the blocks feature, the text feature, the libraries feature, as well as all these different components, which again, label what they are, kind of tell you how they work a little bit as you hover over things and you can see how they work. Really fantastic resources. And something else that I want to show you just real quick before I switch back to our slides here, is if you just want to get started, check out all of these awesome starter programs, right? So if you just want to get started here, I'm going to delete what I have real fast, delete all my things, right? And you want to see what an Arduino circuit might look like or a microbit circuit might look like. Check out these starters made by the Tinkercad team. So if I grab, for example, this microbit program. This has a nice little comment to tell us what this is. It's using a soil moisture sensor, which is super cool. I can check out the code and see how this works. And I can maybe adapt this, I can modify this. And there's an extensive collection of microbit circuits, Arduino circuits, as well as just analog circuits to teach you the basics as you go ahead and build these different projects and things that you can just drag right out into your workspace. And also while I'm here, I'm going to show you that what if you wanted to share this, right? How could your students submit this and share? Well, if you made an activity, they could design and put this in the activity for the class, as I mentioned. You can also press the send to button like so, and you can grab a screenshot really easily. You can send this to Fusion if you wanted to, and this would actually help you if you wanted to make like a PCB using the Fusion's electronics feature to design a custom PCB based on your circuits. You can do that. You can download this, and you can also create a collaborative link where if you wanted to have, for example, students working in a group and you had multiple people collaborating within a single document, they could actually share this link with their group members, and then they can go ahead and collaborate and design, which is super cool. So let's switch back to our slideshow here. We don't have a ton of time left, and there's a couple other really cool things I want to share before we head out for tonight. So I'm just going to switch back to my slides. And again, I want to remind you, I know I demoed that live, and I also want to remind you that that's recorded. So I know I went through some things very quickly, but every single thing I just said has a nice slide like this with key vocab, key terms. So we're going to share this with you as we run through. So again, this will be shared along with the recording with you tomorrow. And as I mentioned, I keep saying, bring your designs to life, right? So some real world insight to one of my classes, a project we did recently, is I challenged my students to make a traffic light, specifically an intersection. So I challenged them to actually, let me rephrase this. I challenged them to fix the intersection outside our school where you're just sitting at that left turn light forever and you can't get into campus. So they did. So they reprogrammed it. They simulated the whole thing in Tinkercad. And then that was a great starting point for them to build this very complex circuit and again, bring it to life using the same components. And it's a really fantastic iterative way to design and prototype in electronics using the Tinkercad program. And also, you might find that a lot of the components have 3D shapes as well. Now, you can't literally take your circuit design and automatically just push a button and have a 3D design. It doesn't work quite like that. But you will find some of the common components like a servo motor, a microbit, a breadboard, LEDs, and they are scaled components. They're locked. So your students might design a circuit in the circuits part of Tinkercad and then prototype some type of enclosure to match that design in the 3D design, and again, use the Tinkercad program to really bring their designs to life and make anything, design and make anything as they go ahead and create here. So as a quick recap, circuits, of course, is a collaborative space for students to prototype and design using real-world components and things that they can actually build in the real world through an iterative process and a safe learning environment. Use circuits to make mistakes, try things out, experiment with things, troubleshoot, and gain skills as they gain proficiency in not only making circuits, but even like learning how to code, learning how to program, as students can bring their ideas to life in a new type of space. And I want to thank all of you for joining us here live tonight. In addition to emailing you with the slides and a link to the recording, which will be posted to our YouTube channel, we're also going to send you a 1-hour professional development certificate for attending this webinar live. So thank you so much for being here with us. And before we jump into our Q&A, I want to bring Randy on to talk about some exciting things happening elsewhere in the Autodesk community.
Right, so we have Instructables here. And Instructables has a teachers page where you go find lots of hands-on learning content, particularly around circuits and 3D design that you can use in your classroom. And we also have contests. And so we have right. We have a bunch of student semester contests. We received a lot of feedback that we run student contests and don't line up with your semester. So we took that to heart and we lined up all three of our contests for this spring to go from February to mid-May. So hopefully that'll align better with the school year. And we have engineering in the kitchen, which I'm particularly excited about. I'd love to see what comes in for that one. And we have a remake it contest where students can find something in their life they think could be improved and build a better version. And we have the ever exciting Made with AI, which is basically use AI to help design and then make something. So it's kind of using AI as not necessarily to build AI systems, but as part of your workflow and to kind of like push your ideas further. So those are the three contests that are student only, and we're very excited to be running them this spring. And we also have a student only fusion contest. So if you have older students, they're old enough to use Fusion, I highly encourage them to enter this arcade contest. Super fun. They can make arcade cabinets, skee ball, like anything vaguely arcade related is open to this contest. It's a very fun one. And we also have the Make It Resilient contest, which is imagining designing, it's an architecture contest where students can use any Autodesk software to basically design structures for uh, extreme environments. Actually, Kellyanne, do you have anything to add to that? I'm putting you on the spot a
Did a
little
beautiful job, Randy, but
bit.
you can
Okay.
design on the Martian plateaus, in the Arctic, in the desert, under the sea. So it's meant to be a contest that helps students think about also just kind of resilient building techniques and to kind of help them introduce them to careers in architecture, engineering, and construction. And we're giving away $50,000 worth of prizes.
Very cool. Very cool. Thank you both, Kellyanne and Randy, for sharing these exciting contest things. And again, I also want to remind you that we did also mention challenges, which is specifically for Tinkercad, and you can check that out on the Tinkercad page, as well as all these awesome Instructables contests for your students to engage with. Looking ahead, we have our next webinar, same place, same time in 2 weeks, called Leap Forward with SimLab, to talk about some of the new exciting features specifically in SimLab. And listen, before we dive into the Q&A, I want to bring all of our faces a little bit bigger here so you can see all these folks that have joined me throughout this evening, joined Randy and I here to answer your questions, collaborate in the chat, the Tinkercad team working hard to make sure that we're providing these awesome resources to you. So a big thank you to all these folks joining us here tonight, as well as a huge thank you to all of you joining us live. And we really appreciate it, and we're glad that you were able to join us for our first Design and Make series, and we're super excited for the many more series and themes to come over the coming weeks.